Welcome back, ladies and gentlemen. Time to go in for the second session of the day. We had a very interesting session in the first half or the first quarter. I think the second part is now a little more interesting, a little more complex, a little more curved. And we start off with Maynard coming in, wherein we have Benjamin Beer, who's going to present a subject of advanced facade engineering at the cutting edge. He's the technical director. He's been with them for the last few years, and he has over 10 to 12 experience in the facade industry. The less I talk about him, the better it is, because his slides speak for themselves. Benjamin, please.
Okay, so many thanks for the introduction. Talking about facades, talking about also the future of facades, talking about energy performance, talking about complex geometries of facades. And also within my presentation today, I'm going to tackle some of the problems that we currently have with facades. And I think this is a pretty important point. Also tackle the problems that we currently have with facade installations on site. So I hope that the PowerPoint's going to load up soon. Yeah. I'm going to start today with a quick company overview of Maynard. Maynard, we're quite a big global group, about 3,500 people worldwide. Out of this 3,500 people, we're about 250 now facade specialists, meaning that 250 dedicated facade staff working globally in several offices worldwide. The main markets are actually Asia, Middle East, Europe, a little bit United States, so this is actually where we work. Now coming to high-performance facade, and I think it's pretty important to understand high-performance facade and what the future is going to bring us in terms of high-performance facade. It's important to understand the past, because also in the past, people have been smart, people have been evaluating facades and building systems over a very, very long period of time, and it's pretty important to look backwards and really pick up items and to say, are there any items that we can utilize today? So I'm going to start with my slides. So this is a project in Central Europe, a kind of cold climate. So this building, it's about more than 250 years old. So also the facade is 250 years old. So this facade has actually resisted all of the time. A lot of people nowadays talk about green buildings. Now, looking at this building over here, it became over the years so green, it actually disappears within the green environment. So this is, I personally think, a pretty good example of a kind of green building, of a high-performance facade designed in the past. And if you look at the specification of this more than 200-year-old facade, it's actually double-skin windows. So over here we have 2 layers of glass and 2 layers actually of windows. We have operable natural ventilation, meaning we can open the internal window to get some fresh air in. We have external shading over here. People can flap open and close. So during the summer, I might just flap and close. We have internal shading over here, so actually blinds for privacy. So also this facade, you can adjust the U values, so the kind of thermal conductivity can be adjusted by opening the inner and the outer leaves of the glazing. It's low maintenance, environmental responsive, produces accessibility, so all timber, and it's also biodegradable. So I think also we need to see that this was a high-performance facade at the time it was built, and this facade survived all of the time. Now going from a bit of colder climate to a kind of hot climate as it is over here, and I think this is pretty important to understand. We have a very specific climate here in the Middle East, which is very hot, relatively humid, and high dust and sand in the air. So when we think about a facade design, it has to be specific for the Middle East market. I'm going to show some slides later on. Now this is what people have done here in the Middle East in the past. There was no electricity, no air conditioning. So they picked up the wind by these wind towers. They brought the wind into the kind of courtyards. So people used relatively, nowadays we say this is simple technology. At this time, this was actually high technology. Going to the next slide, people had windows, people didn't have glass, so they had a kind of shading, this kind of mashrabiyah styles. So these kind of windows that let air going through, a bit of fresh, cold air, but at the same time, they actually provide shading. In the past, in the Middle East, people have built houses relatively close next to each other. When we get natural shading by the building adjacent, so we have relatively small walkways with shading. So all of these kind of things was actually how smart facades have been in the past. Now, people tend to ask, why can't we do the same thing nowadays? Why can't we just replicating these facades, these kind of buildings? And this comes back to the main topic of thermal comfort of human beings. And we have to keep in mind, in the past, people lived over here with no air conditioning. So people lived by 40, 45 degrees Celsius in the summer. So how did it work? This is some testing being done in 1943. So actually, the US Army put people into a test room and heated up the test room. And this graph is showing actually the heart rate and the skin temperature of the people. And you can see that this kind of graph is actually going down. So for the first couple of days, or for the first 3 to 4 days, people are sweating, people do feel uncomfortable. But starting after 5 days, people do acclimatize to the higher temperatures. So you can see that this curve then goes down, it goes into a horizontal line over here. So people do acclimatize to higher temperatures. However, this is not what we can do nowadays, because all of us, we're all used living in air-conditioned spaces. So right now, there's no way going back. So we need to build smart facades for the nowadays environment and the nowadays thermal comfort of our human beings. Now looking into energy efficiency, and this is a pretty important item, the main energy consumption of buildings in the Middle East is actually the cooling loads. We need to cool our buildings down almost the entire time of the year, which means we put a lot of electricity into the chiller units on our buildings. If you look what kind of influence we have as a facade designer, it is mainly a couple of items. It's first of all reducing the solar heat gain, but why doing that, actually reducing the solar heat gain coming through the facades? We need to think about the thermal comfort of human beings. And this is a couple of points over here that we as a facade designer, as a facade consultant can actually influence, which is actually radiations, air temperature, air movements, but also pretty important over here, it's a visual comfort. And this is another item which comes back to the kind of visual comfort of human beings. So people want to look outside. The main reason of putting glass into our buildings is that the human being, we need light and we want a vision to the outside. And this is why we still have nowadays this kind of fully glazed facades, this fully glazed boxes, this kind of floor-to-ceiling glazing, because this is currently what the people want. So it's actually for us to tackle all of these issues and getting the facade more energy efficient. And even today, we've seen a lot of presentations about future facade, very revolutionary new products getting into the market, switchable glazing, double skin, complicated stuff. But what we say, even with the current technology, what's pretty important is that choosing a good product, especially for the glass. Now, the whole glazing industry, so what's the glass doing here in the Middle East? So we want to have glass that lets through a very high percentage of natural daylight. At the same time, our glass should have a maximum clear vision because we want to look outside, especially in our high-rise towers with a nice view. However, at the same time, our glass shall minimize the solar heat gain coming through the glass to the inside of the building. And this is why we call a highly selective solar control glazing. So the selectivity is called that we select certain wavelengths out of the solar spectrum coming from the sun, and we let through the visible daylight through the glass, but we keep out the solar heat gain, which is another wavelength, which is more the radiant heat. And this is all about selecting a good glass. Now, starting with the history of solar control glass, we started with actually so-called single silver coatings. We then went to double silver coatings. Nowadays, we're having triple silver coatings. So this is kind of state of the art. And just by selecting a good triple silver state-of-the-art solar control coating, we can reduce the solar heat gain of a building between 10 and 20% while having the same amount of daylight coming through the glass. And This is a problem what we see quite often. Things are getting value engineered out, and also Lars mentioned this actually earlier today. And what we trying to explain to clients, to architects, is actually when you buy cheaper glass in the beginning, and this is this thing called life cycle cost analysis. If you look at the complete running time of the complete life cycle of a building, yeah, we're going to speak about 30, 40, maybe 50, 60 years. So you're going to save a little bit of money over here during the construction phase by selecting a cheap glass, for example, single silver glass that lets through about 20% more of solar heat gain while having the same amount of daylight coming through. If you then look at the kind of cost, and about 80% of the life cycle cost of a building is the operational cost. So if you spend a little bit more money over here, and we're just speaking about not a big amount per square meter of facade, you're going to save a huge amount of money during the operation time of the building. And we need to keep in mind that our glazing is going to be there for the next 20, 30, 40 years. So all of the next 40 years of this life cycle of a building, the operator of the building will spend more money on cooling this building down. And this is what we think is pretty important, is first of all, it's a green building design, spending slightly more money over here, and it's also saving costs for the operator for the complete life cycle of the building. Now coming to my next topic, complex facades, complex geometries. These are just a couple of built examples in the Middle East of Meinhardt projects of curved, twisted, two-way curved facades. Just a couple of images over here. And Meinhardt facade, we set up a certain technology of classifications. How can we classify this different curvature, and how can we technically clad these twisted and curved buildings? So this is a kind of guidelines that we actually take to the architect and sit down with the architect. We want to achieve a curved facade in a cost-effective way, so cost-effective and technically good way that is watertight, airtight, durable, and so on. So we sit down at very early stage with the architect. We go through the options. What can we do? Either code banded, shifted louver, fish scale, and so on. So this is just a kind of methodology. And then actually the architect together with us is actually choosing the best way forward. I'm going to show a couple of project examples. This is a 550-meter tower in the Middle East at very early design stages. You can see the current architecture is going to more complex geometries. Looking back, the kind of high-rise tower started as a kind of box building, four-side box going up and down. Whereas nowadays, the architecture is looking more into complex geometry, curved geometries. Then we step in as a facade consultant and we look how can we realize these curved geometries. We do intensive 3D parametric modeling. We look which areas are actually critical in terms of curvature. For example, here there's a kind of wet areas here and here. We then model this in our softwares. We go through the details, so we get this freeform shaped surface from the architect. We then put a point grid onto this freeform surface. We then put a facade grid on it. We go through it step by step, and then the image over here is shot between green and red areas. And the red areas are, for example, these areas where the code band limits do exceed the current technical ways that we actually saw, meaning that the red areas currently are technically not possible, which means we then go back to the architect. We either start remodeling the geometry of the building to fit our code banding limits. So we say we want to build a cost-effective facade. We know the code banding limit is this amount. So we then started remodeling the complete building geometry in a way that it can be easily clad cost-effectively with our facades. And this is a kind of step-by-step process. On the left-hand side, the architect's intentional vision. So actually on the left, we have the kind of architect's idea. We then put on the kind of facade grid, vertical, horizontal grid, and we start reshaping, remodeling the cladding. And you can see this is the kind of final end result, which is smoothened out. And this result over here is actually fully within the code banding limits of the facade. So this is on the right hand side kind of comparison between the original and the new kind of outlines. This has to be done at very early stage because we touch the complete building geometry. We also slightly modify the slab edge positions and the spaces. So this is a point where we work very closely together with the architect at early stage. Just a couple of images showing the kind of 3D curvature. We push things in, we put the facade grid on, spandrel panels, glazing panels, and this is all fully parametric, which means we have a parametric software running within our 3D model. So even if the architect is changing the base model, for us it's quite often just a click of a button to rerun the model and give them the perfect facade geometry and actually the perfect facade grid. Just a couple of more images, base geometry, proposed geometry, and just a kind of overview step by step, what we do, and also how we do it for this job. Now, speaking about a kind of build example, and this is to our understanding, this is just almost finished on site. This is, as far as you know, one of the biggest projects worldwide with the so-called code-band facade. A lot of people speak about code-band facades. We built these things. And again, we went through the design process and actually analyzing the geometry by the architect, this free-form shape. We built a parametric model. We did actually the analysis where's the maximum of curvature, where's the maximum of warp and code banding on our unitized facade panels. So we came up with this image over here. Then we have our kind of software parametric where it actually runs through this kind of steps, analyze our facade. And then on the right-hand side, this is actually the project being built. We code band flat pieces of unitized facade panels up to 135 millimeters, which is quite a lot. It looks a bit scary. And this is why we did a lot of internal testing, scientific analysis, especially on code banding with structural silicon glazing, because our glass panels on this project are held in place by structural silicon. So we did this kind of testing, and I hope you can see here, within our panel is flat, so everything is flat. And then on the side, you winch the panel into position. You can see how this is then pushed by force into position. So this looks a bit cool, but this is all tested. It's tested, checked, analyzed, and it's also durable. So actually, by doing that, you need to keep in mind that we have long-term stresses on the glass, on the aluminum framing, and the silicon. So all needs to be designed actually for doing that. So this is just a kind of photo how far we did code bend the glass during the testing. So we've done stress testing for the silicon, for the glazing, for the framing. We also developed a couple of new approaches how we design the structural silicon for code bend facades, because currently there are no design guides out there. There's not a code, there's not an American standard, no European standard. So we set up the standards on our own. We published certain technical approaches. We discussed it with the silicon suppliers on the stress model, on the design models, how we do it, what's a safe way. We published this at several magazines, publications. So we set up a complete new design concept for code band structural silicon glazed unitized facades panels. So this is pretty groundbreaking, and I think we have to push things ahead. And this is touching slightly about the future of facade. So getting the future done nowadays, we need to push current technology. We need to push suppliers. We need to push the design approaches. And you have to be sometimes a little bit of brave, speaking to everybody and pushing these things ahead, because a lot of people have concerns. Now going on to my next topic, quality control. And especially here in the Middle East, the truth is that not a lot of, quite often on site, things do go wrong. So we think it's pretty important having quality control on site, having it on site and also looking what's happening on site. And this is a very nice example of a project where the designers, it wasn't us, did not take into account the local climate conditions in the Middle East. As I said before, it's hot over here, it's humid, and we have sand and dust in the air. And you can see all these kind of dirt strikes going